Alright, we're back with section 3.7. This is implicit differentiation. This is problem number 4 from the 3.7 assignment. If you have not watched my conceptual video about implicit differentiation, I would highly recommend doing so. It's a little wacky at first. It'll seem a little weird. But essentially what it is, most of the functions we've dealt with in algebra and calculus up to this point, like some polynomial, y equals x squared plus 2x, you can separate the y's and the x's. So in other words, we've got one y on this side, and the other side is entirely x's. Well, with a lot of equations, you can't actually get y on one side and the x's on the other side. And if we want to know how to take derivatives of those equations, we need to learn implicit differentiation, which is the form of differentiation used if you cannot get y on one side and only x's on the other side. So this is one of those cases. Now what we're looking for is dy dx. But as you'll notice, the y is stuck inside of this sign. So what we're going to have to do is implicit differentiation. And like I said, if you haven't seen the first video on it, I highly recommend it. So I'm going to take the derivative with respect to x of the left side, as well as the derivative with respect to x on the right side. Alright, and let's see how we go about this. So the derivative of e to the 7x, using the chain rule, the derivative of the outer function, the derivative of e to the anything is just e to that thing. So the derivative of the outer function is e to the 7x, but to respect the chain rule, we have to multiply the derivative of the inner function, which is 7x, and the derivative of 7x is 7. So using what we know about exponentials and chain rule, we were able to take the derivative of this side, 7e to the 7x. Alright, now we'll go over to this side. The derivative with respect to x of sine of some variable, so we're taking the derivative of the outer function, would be cosine of that same thing. So, like the chain rule states, we're taking the derivative of the outer function without taking the derivative of the inner function. But now we're going to multiply on the derivative of the inner function. So we're multiplying the derivative of the inner function onto this outer function derivative. The derivative of the inner function here, using the power rule, the derivative of x is just 1. So we have 1 plus the derivative of 9y. Well, the derivative of 9y is just 9, because the y loses a power according to the power rule. However, because y is a function of x, so this is at the foundation of the chain rule, because y is a function of x, right, that's why we're finding dy dx. Implicitly, there is going to be a function inside y that's in terms of x. So if we're going to take a derivative with respect to x, we also have to respect the fact that y is the dependent variable and x is the independent variable. So where you see a y here, I want you to imagine there's a function of x. And in order to take the derivative of the inner function, according to the chain rule, we have to take the derivative of y with respect to x. So think of the outer function here as 9, and we took the derivative of the outer function. Now we need to multiply the derivative of the inner function due to the chain rule. And so we end up with this expression. Well, now our goal is we're trying to solve for dy dx, so we're going to have to do some algebra. Let's go ahead and divide the cosine x plus 9y over. So we'll end up with 7e to the 7x over cosine x plus 9y equals 1 plus 9 dy dx. So the next move is to subtract the 1 over. I'm just going to do that right here. So we subtracted the 1 over, and now we need to divide everything by 9. So we divide everything by 9, and we've solved for dy dx. Now you could probably simplify this some, but you can just plug this in. The important thing here is that, remember, we're using implicit differentiation because we can't get y all on its own, right? Because we can't get y on one side and x on the other side. So it makes sense that the derivative of y with respect to x no longer has only x terms. You'll notice there's some y terms in here too, like 9y. Whereas with explicit differentiation, which we've done already, our derivatives always were in terms of just x. Well, now our dy dx depends on not only x, but also y. And so that's a telltale sign of implicit differentiation.